Can you hear me? Yes. Thanks for the introduction. So, okay, we'll skip then this part. So you might be wondering where this software come from. And well, it actually started with a European project with a pretty good balance of academic and industrial partners. We have NTNU in Trondheim in Norway, Almeria, University of Almeria in the south of Spain, Aalborg University, and in the industrial side we have BCC Financial Group, also in the south of Spain, Daimler, the car manufacturer, and software, the Hugin Expert, which is a software company specialized in Bayesian networks. And this is actually our team of developers and scientific members. Some of them were here last year, and they got really good ideas for what we've done. And the way I would like to introduce the toolbox is through a use case. So we were approached by our BCC partner, and they told us that they had this problem, that they wanted to predict defaulting clients, to know within which of the clients will default in the following 2 years. And until now, they were using a logistic regression model, so that their goal was to improve the performance. So we said, okay, that's a pretty good problem, and should be relatively affordable. So they started to show us the data, and they told us that so there were client financial operations coming every day, records appearing every day, and millions of clients. So we needed a scalable, but also distributed setting. This data also had a lot of missing data, and that's quite challenging for traditional machine learning techniques, such as logistic regression, for instance. But also, we found that there were quite odd distributions like this. So they were zero inflated, and that can happen. For instance, some clients don't perform they don't get any money from the ATM in a particular day. But also, there were very high values, so the distribution has very long tails because there might be clients that actually have a lot of a high amount in the total credit amount. And at first we thought, okay, this might be outliers, we can just forget about them. But they told us, no, these are actually clients that are very interesting for us, so we want to keep them. So, well, before I continue, I'm going to give an overview of the toolbox. So we use, as a model, we use probabilistic graphical models with latent variables, and we use a probabilistic language to create these models. Then you just put your data there and learn a learning engine, then just learn the model for you. This learning part, that is contains the highest computation. You can do it multi-core or distributed, using distributed processing using Flink. From a more general perspective, so what you have is an open box model. That's the probabilistic graphical model that you can customize. You can you have control over it. You can put some links and incorporate expert knowledge. So let's say you have a bunch of data, a lot of data, and regardless of the model you specify, there's going to be a black box inference engine that we provide, and that's powered by Flink, that's going to learn this model, and then you can just get some knowledge. And I will get into what this knowledge is later on. So the main features of the toolbox, and this is one of the key ones, is that we use latent variables. And these latent variables are used to model things that are in the part of the problems that are there, but that you cannot directly observe. An example of this could be in a sickness. So we're able to observe someone's symptoms, but we are not able to observe directly, which is the sickness. So we will model the symptoms based on different observations, attributes for that, and we will place latent variable for the signex. In the context of the financial data, so what we cannot directly observe is the financial health of a client. But we can observe some financial indicators, such as what's the salary this client gets, the amount of money at the end of the month, that will give us an indicator of what's the financial health of this client. And that's very relevant, because actually if your problem can be modeled using this type of latent variables, then this toolbox can be of interest. Otherwise, there might be other machine learning toolbox that could be more fitted. So just let's recall the financial data. This could be, please don't run away. This could be the model that is the model we've used for the trying to predict if a client is going to default or not, and that's actually very easy to understand. So here we have the different financial indicators, the ones that we can observe for each client. We also have a class variable that is telling us if this client is going to default or not, but you may or may not observe this class. So data points may or may not be labeled. Actually, for the kind of learning that we are doing, that's not relevant. It can learn regardless. We placed a number of local hidden variables on top of the predictive attributes, and these are used to so more technically to use mixed set of Gaussian distributions instead of just Gaussians. And what that means is that you have clients that are doing different things on different days, and that's very normal. So you have that there are no transactions on some days, and maybe some other days it follows a normal distribution, and that happens for the different clients. So that would be modeled through the local hidden Gaussian. And then we also place this other Gaussian that's shared among the clients, and that's used to model the dependencies between the observed financial indicators. That meaning that usually a client that makes a lot of money or that has a high balance at the end of the month is more likely to perform more operations with a credit card. So we need to have into account. Then there's also this external global hidden variable or global parameter, and that's used to take into account the aggregated information among all the clients. And this, with that global variable, you could get the probability distribution of the different group of clients. And we don't know what they are, but we don't know that they are there. So that's what the piece of code from the user perspective looks like, and it's rather easy to follow. So we just have to set up the Flink session, first of all. Then we will load the data, just specifying the path of the data that could be in an HDFS distributed setting. Load this data, and what you notice here is the data Flink class, and this is just a wrapper of the data set of Flink using a set of data instances for each of the samples of the operation of the clients in this case. This data Flink is also extended to use to incorporate information about the attributes. Once the data is loaded, you just have to create the model, and for that, in this case, you just call this class custom Gaussian mixture that creates this model for you, specifying using this probabilistic language to specify the different nodes and the links between the nodes. Okay, so now once we have the model, what we want to do is to learn from the data we have. And then the way we do this is by resorting to Bayesian approximate inference. What are the differences between Bayesian inference and Bayesian learning, which is basically the same in the Bayesian context, and doing traditional learning? So for instance, in a logistic regression model, what you get is a point estimate, a weight for each of the attributes, right, a 0.7. with the Bayesian learning, what you get is a probability distribution that is telling you something about the certainty of what you've learned. So for instance, if you get a normal distribution of mean 0.7 and a variance, a very large variance, well, you know then that you might be a bit cautious, because if it's a large variance, it's that you are not very certain about what you've learned. And the other way around, if you get a very small variance, then you know exactly what you got. Another property about the Bayesian learning is that it fits very naturally with a streaming setting. So as more data arrives, you can update your model automatically using the Bayes theorem. So, well, this being a bit more technical, so the way we've coded this into the toolbox, in the AMIDST Toolbox, is that we use a variational message passing algorithm. That is, it is the state of the art for approximate Bayesian inference. And we have adapted this algorithm to use it in a distributed setting. And that was very easy to do with Flink, because we just used the iterative data set and did a map, used the map reduce functionality for that. We also used the convergence criterion, and you can choose various. You can choose to stop at a certain time or after a specific number of iterations. The way it looks, so when you've created a model in the toolbox, you just call this method, update model, with your data, and what's going on behind the scenes is all these Bayesian learning algorithms, okay? And that's black box. It doesn't matter what's the model you have specified, that's going to be done that way. So another demand of the BCC institution was that the model should be updated every day, and this update should be done within a 3 hours time frame. So in order to do that, well, that was we resorted to this Bayesian learning update, and that was easy to reach. So this is how it looks in the data. Imagine that you have data. We ended up not doing it every day, but doing it every month, because it was not that interesting to use that finer granularity, but it is the same thing. So if you just, the way you have to do it is just load your data every month. And I forgot to say that the format that the AMIDST Toolbox uses right now is the R format, and you can read more about it in our webpage, but it's just an extended version of the CSV format. And so you just load your data for each month and update the model. And what's going under the scenes, again, is the Flink doing the distributed learning. So all this work, we put it into practice for the BCC problem. And well, what they got with the logistic regression model was a AUC of 0.81. And we were able to get an AUC of 0.95. That was beyond the 0.99 goal that they had. So they will put it into production at the end of the year. I'm going to talk about the scalability. I'm going to show you also the scalability analysis we made. And for this part, the BCC group, they have their own servers, and that's the only place where they can, of course, run the models and have the data. So the other experiments were made on a representative sample of 55,000 clients. But we wanted to use a distributed setting, and so we resorted to the Amazon Web Services for that. But then the BCC group, they just provided us with a script to generate data that was similar enough to the data they had. So we sampled 42 million clients, and we used on the Amazon Web Services, we used a cluster of 2 nodes, 4 nodes, 8 and 16 nodes. And what we got, so in the x-axis, you get the time. In the y-axis, this is a measure of quality of the model. So what you can see here, it's, let's say you're happy with this quality. These are just the different iterations of the different updates of the model. So let's say you're just happy with this. Then if you can afford to have a 16 node in AWS, then you can reach that point in 3.5 hours. But else, if you can afford only to have a 2 nodes cluster, then it will take you more than a day to reach that point. And the scalability graph, the speed up graph looks this way. So what we show here is the difference between the time used for 4, 8, and 16 nodes with respect to the one with 2 nodes. We see how the scalability keeps going up. Of course, there will be a moment where it will flatten, but we haven't actually reached that point. Actually, the sequential part of the distributed approximate Bayesian learning algorithm that we have used is very minimal. Well, this is just a slide to show that we use a very modular design just in the fashion of Flink. So it's quite easy to maintain and also to incorporate new algorithms and new functionality if anyone is interested. We've integrated this AMIDST Toolbox with other software like Moa, Weka, and our partner Hugin as well. And this would be the Maven modules. The core and the core dynamic modules are the ones that contain the main functionality of the toolbox. We use the Flink link for the distributed part, but mainly that's some other examples. We also provide, so in case someone doesn't feel very comfortable by specifying their own probabilistic graphical model, then we provide out-of-the-shell models, well-known ones like hidden Markov Models, Kalman Filters, naive Bayes, and a bit more complex ones that you can use. This is another use case, a bit more advanced, and this also, that's the last one, that was motivated also by the financial institution. So they just asked us to monitor the profile of the clients during the Spanish financial crisis. And for that, where they had data from April 2014, in April 2007 to March 2014. The model we used for this, and this is again very easy to interpret, is this dynamic model. We have this is a slide that is replicated for each month. And we have a naive Bayes sort of structure with the financial indicators and the class variable. But the key of this model is this latent variable here. And this latent variable is connected through time. The purpose of this latent variable is to capture the changes in the customer profiles through time. So we explicitly represent the dynamics of the problem in the model. This is how it looks in the toolbox, in the code. It's pretty much the same as before, just set up the Flink session, load the data stream. And now here, when we build a model, instead of using a custom mixed Gaussian, we just use a concept drift detector. And that's creating, under the scenes, is creating the model I showed you before. Every month, we load the new data and just update the model in the same fashion. The only difference here is that now we need to query the local variable that we've specified. The meaning of this local variable is if we get the same value throughout the time, that would mean that there's no concept drift, there's nothing going on. The profile of the customers is actually not changing. But if there are some changes, that means there's something going on. So when we plotted the values of this age along the months, this is what we got. We quickly observed a general trend, how these values are going up, and that would be explained by the financial crisis itself. It's going pretty bad until there's a moment that it flattens a little bit. But then there's another seasonal trend, and actually the reason for this trend is the type of economic activity in this region of Spain that is mainly based on tourism and agriculture, and it of course vary depending on the time of the year. We did this work in collaboration with close collaboration with the financial institution, the BCC group. So we decided also to plot the unemployment rate in this region in that particular period, and we shifted it 3 months in the past, and what we observed is almost a perfect correlation. The Pearson correlation coefficient actually got us 0.96. So it was clear that the unemployment rate was actually a main driver factor of the concept drift. That's pretty much what I wanted to show you. We have a brand new web page that I think I have time. It was very quick. So this is our web page. You can find more information here, documentation, and we also have a blog where we, so there's only one entry now, but we plan to, all the scientific papers that we publish to explain them there in a very friendly manner. And yes, all the code is open source. You can download it from GitHub under the Apache license 2.0. So if you have other commercial code, you can actually incorporate it and use it as well. And well, just to thank the Flink community for inviting us here and everybody for attending. And we're very happy to get more use cases, more users, more collaborators. We're very interested in, so we sort of used Flink as our distributed, for distributed computation, because when we started, the machine learning module was not very well developed, so we just decided to go our own way, but it will be very interesting to incorporate this probabilistic machine learning capabilities into the machine learning module in Flink. And yes, please contact me or any of my colleagues if you have any doubts. And thanks. That was very quick, so if you have some questions.
Thank you. This was a very interesting talk. I wonder if you tested against any other methods, for example, XGBoost. That's one question. Another thing is you mentioned it's possible to use your method to learn from the stream and not a batch training. So I wonder if you tested the quality of the predictions if you only do a stream-based testing, training.
So we do, yeah, I think I didn't say it clearly. With respect to the last question, we do streaming learning, but we use the batch Flink API, okay? So the model can be updated as new data comes. We've compared it to other Bayesian approximate techniques, but we actually, because it's really not that easy to find open source out there that it's, the use is streaming learning for the model, but we're open to hear about other source, open source code and do some comparisons.
Any other question?
In your implementation of your the algorithms, do you use the streaming API of Flink?
No, we don't.
Okay.
No, we
Because
actually, but it could be easily adapted to use the streaming API from Flink. But we use the batch streaming.
Yeah, because
but we do it in a streaming fashion. We just distribute, update the model, and you can choose the granularity.
Learning is the most natural use case for streaming, right?
Yes,
It's natural to reason about. I wonder whether you can gain some performance boost if you implement using
the
streaming API
That's a
of
good
Flink.
question. That's a good question.
Okay.
Yeah.
Okay. Hopefully you can answer it next year.
Yes, yes. Thanks.
Wow. Perhaps you can talk a little bit about who uses the toolbox and how you kind of, apart from this talk, how you make it, more popular and help to get more users, because maybe the Flink community can learn from that as well.
Yeah, that's a great question. This is our main use case. We've just sort of started, and we are willing to get more use cases. Actually, that was one of the reasons to create the webpage, and we are now attending many conferences and very willing to attract other real use cases. But yes, right now we're mainly using it for research and for this financial institution. But we hope to grow fast.
Okay, I have a question. How do you differentiate between concept drifts and outliers, maybe, in the user profile when you are talking about transaction? Because because both changes and outliers could be something very different. And
the way the toolbox treats outliers, or it's able to handle outliers properly, is by using this mixture of Gaussians with the latent variables. So you, instead of just assuming a Gaussian, where you leave out all these important points, so you place a Gaussian here, another one here, and another one here, and then you take into account these outliers, okay? And that's the natural way. Does it respond to your question?
Yeah, more or less.
More or less?
Yeah. No one wants the box?
Okay.
So, okay. Yeah,
Well, thank you very much.
Yeah.